then.
Yeah. 4 times the one I had before.
Yeah.
This should do it.
You have animal behavior and weird things happening with the rocks, the ground heaving up and down. There are other ways we can try to get at least an idea as to the likelihood of earthquake activity in the future. And that's through the use of what's called seismic gas. And this is one of the main reasons why seismologists study this, scientists study earthquakes. Why they want to know where that focus was. They want to know where on the fault those rocks break loose. We track that. Over time, we'll keep track of where earthquakes have occurred on a fault. And over time, what we'll see is that that fault will experience all kinds of earthquakes over time. But there will tend to be 1 or 2 regions that aren't seeing any motion. This whole fault can be absolutely lit up with quakes on top of quakes on top of quakes, is constantly moving and popping, except for one region. That region is called a seismic gap. What that tells scientists is that that region on the fault is the area that's building a lot of stress. And the longer the time passes where there is no quake there, the more likely there will be one. So the tracking of seismic gas at the very least gives us an idea of where the next quake will be most likely. And the longer that goes without a quake, the higher the magnitude we know to expect. So with seismic gas, you can get forecasts, predictions of most likely where. That would be somewhere in the gap. And what magnitude? Because the longer that goes without motion, the more stress accumulating there. And the more stress means the more energy that will be released when it finally pops. It's mostly from the investigation and tracking of seismic gap information that seismologists can have earthquake forecasts for California. For example, they are expecting in Los Angeles a magnitude 7.5 to 8.5 within the next 15 years. Now, the longer the time passes without that quake occurring, the lower that number of years expectations decreases. Now, that quake can happen tomorrow, or it can happen in 14.5 years from now. That's about the best we can do. There have been some research and some investigations, some trials done with warning systems that would relay a radio signal of impending earthquake energy. They could give people anywhere from 30 seconds to maybe 2 minutes warning. Some argue that would be enough time to turn off the gas, turn off the electricity, turn off the water, pull the car off the side of the road, get under a table. Others argue in 30 seconds you would incite so much mass panic that your casualties would triple. So.
What really can you do?
Well, if you're at home, 30 seconds, you can at least get up and turn the gas off. That would be helpful. It would help maybe save your house from fire. And you have time to maybe grab your dog and get under a table and kiss your rear goodbye. 30 seconds. If you're caught in traffic, Los Angeles traffic, in 30 seconds, you might as well, get a smoke and enjoy yourself. Yeah, do it. Yeah.
You said that it could be from tomorrow to 15 years. If it takes to the 15 years, does that mean it will be greater magnitude, or does it determine?
Well, if it exceeds that weight expectation, they have to reevaluate and look at seismic gas. If there's been any activity in that gap, and then narrow down the focus on that gap. Because gaps get bigger and smaller through time as well. So you may have in that interim smaller quakes that maybe kind of fill this in a little bit. Narrow that gap down. But the longer it goes without motion, usually the bigger the magnitude. Because it's getting more and more stress as everything around it breaks loose, but it's still stagnant. Any other questions? From moving ground to water. This is the hydrologic cycle. The hydrologic cycle is the constant circulation of water, thus, hydro, throughout the Earth's systems. The Earth has many systems, many cycles of complex processes that all overlap and interrelate with each other. We have the lithosphere, solid earth, rocks, the ground. We have water in the oceans. We have water on the land surface. This is all your fresh water, your rivers, lakes, ponds, wetlands. You have water underground. In geology, we call that groundwater.
Very scientific.
We ran out of names. We'd already used that Latin for something else. We have frozen water, glaciers. Oh, the atmosphere. We have the atmosphere. And we have us. The biosphere, living things. Lithosphere, solid earth. There are multiple minerals that contain hydrogen and oxygen in their chemical formula. When those minerals melt, the hydrogen and oxygen are released, and they are then able to recombine with each other to form water. That's the source of water, and especially steam, in magma. So we know we got water actually in the minerals and rocks. We've already looked at that, and I mentioned that multiple times already in class. Oceans. In this class, we don't have enough time to really look at oceans in any great depth. We'll be focusing most of our look at oceans, where oceans interact with the land, coastal processes. To really understand ocean processes, that's another 16-week term called oceanography. That's a whole field of earth science. You can spend 8 years studying to be an oceanographer. We got 6 weeks left. So we're going to defer that to a different branch of science. The land surface, we'll look at that next, looking at fresh water, especially rivers, streams, and the role they play on the land. Later on, probably next week, we'll be looking at groundwater. That's water that exists in the spaces and nooks and crannies and passages in the rocks and the sediment under our feet. Glaciers, frozen masses of compacted snow and ice that tie up a substantial amount of the world's fresh water. We'll look at those probably in a week or so. The atmosphere, we have moisture in the atmosphere. We'll know that over the next couple of days. The rest of Hurricane Patricia rains all over us. The atmosphere, we won't be addressing atmospheric hydrologic cycle in this class. That's another branch of earth science called meteorology. And again, that's another 6 to 8 year adventure to become a major in meteorology. So that's beyond the scope of what time we have left in this class. And biosphere, that's all living things. Your body itself is about 80% water. Which is, I had asked a question one time in one of my classes years ago. What's happening to the Earth's water? And because one of the things that's happening to it is getting redistributed, different parts of the cycle, it's not getting back to where it was. So access to water is getting more difficult for some people. Sea levels rising because glaciers are melting, but the availability of fresh, drinkable water is dwindling because of pollution issues. And one of my students came back with a good thought, said, look, it's tied up in people. You know, at the time there were 6.5 billion people on the world population estimate. So that's 6.5 billion people full of 80% water each. Plus all your animals and all your plants, that's a lot of stored up water. And now there are 7.3 billion of us. That's a lot of water. I guess if you're thirsty, something in, drink your arms. Yeah, kind of. I would, wow, yeah, wow. But biosphere, there's a huge amount of water that circulates in and out of the biosphere, out of living things. And again, it's a little bit outside the scope of this class. If you want to learn more about that, you can take biology. Again, interrelated sciences here. But it's a cycle, much like the rock cycle. There's no start point. There's no end point. You just jump in and go. There's artist's renderings in your book, in one of these interludes. Interlude F, page 580. Page 580. Isn't that awesome? Where's that from? This is your basic hydrologic cycle, showing arrows going in and out and around and back and through. You know, if you have glaciers melt, that melted water gets into streams and rivers. Streams and rivers will allow some of that water to soak into the ground and join the groundwater. Some of it's going to be evaporated into the atmosphere, become clouds and precipitation. Some of that water will be taken up by plants and animals. And in a big river, some of that water will go all the way back to the ocean. Because the ocean evaporates, turns into rain, and it goes around and around and around and around and around and around and around. Now, hopefully, having been in geology for 10 weeks now, you have a better sense of how things all connect. That there's really not a whole lot on this planet that you can do to one thing and not have it have an impact somewhere else on something else. Cycles, everything's connected. Systems, everything's connected. This is a concept that really was not even considered back in the 50s, 60s, even into the early 80s. One of the popular taglines for industry and politics for the longest time was dilution is the solution to pollution. The idea that there was no way any human activity could possibly impact the natural world. The natural world's just too big. So it was common practice for industry. If they had leftover chemicals and stuff they didn't want, just dump them in the river. They would get diluted, they would flow out to sea, and there's be no problem. Well, unfortunately, they are a problem. And they didn't give any thought to the fact that river is going to also pump those hazardous materials into groundwater, which people are going to try to drink later. If it gets to the ocean, it'll crash resources for fisheries, and people will lose their jobs. You'll have contaminated shellfish that nobody can eat for decades. And that some of that can evaporate into the atmosphere, potentially contribute to widespread air pollution. That it can soak into nearby soils to make fertile farmland absolutely useless. It was completely that things could be connected that way. But they are. The Earth is a self-contained planet. What goes around comes around. It has to constantly use and reuse what it has because it can't get anything new from anywhere else. The Earth has no Walmart. Earth supplies everything in the Walmart, including the Walmart. So remember that. Today would be a great day, today or tomorrow. You get stuck out in the rain, with no umbrella. You get all stuck away. The next time you take a drink out of the drinking fountain, or you brush your teeth, or you take a shower, or you use the toilet. Think about how many times that water's already been drunk. How many times it's already been flushed. That could have been camel sweat, dinosaur spit. You could have sneezed the same water out of your nose when you were 3 years old. It's the same water. This could have been part of a Snapple 5 years ago. It's the same water. You'll never be outdoors without an umbrella again. Ew, it's totally not me, ew! It's the same water. It just goes around and 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 around.
I don't think this is going to encourage us to drink more water.
Drink Dayton water. Southwestern Ohio's got one of the world's biggest groundwater aquifers, and Montgomery County does a hell of a good job, one of the best jobs in the nation, keeping that water safe and high quality for drinking. It's one of the best water in the nation.
Don't they tell you that Carolyn Park that they have right there?
I think they do.
Park is
Yeah.
one of the best offices in the world.
Yeah, definitely. Yeah, right underneath. But we're the biggest too. Yeah, it's good for us. I think it's good for us. Water in this part of the nation also tends to be hard water, meaning it has a lot of dissolved calcite in it. But studies have shown that increased calcium is good for your ticker. It helps reduce the risk for heart disease. Southwestern Ohio, and of course in another study, we're all way too overweight, worst in the nation. But our water's good. We won't die from heart disease. We've got one of the lowest rates of heart disease because of the calcium in our water. So it's good for you. Healthy too. It's already been used millions and millions of times over. Yeah, that's great. Great question. That's why we have I see a lot of people with a lot of caffeine today, different versions of caffeine or sugar. Yeah, and that kind of a weakness also too. If you have a bottle of something and you're not going to finish the rest of it, empty it down the sink first. Don't throw the bottle away with water with liquid in it, because that liquid is mostly water, and we don't need to be burying water in the landfill. So put it back down the sink so it can come around again, and we can make something else with it again or drink it again later.
And then we can shower in it, right?
And then you shower in it and flush the toilet and clean it out, and you'll be all set. Oh, wait till we get to groundwater. I got such gross stories from people. Oh, I can hardly wait. I want to tell them all now. I have to wait. I have to wait one.
We're not going to be talking about food much.
You're not going to want to eat or drink for the next 3 weeks. You're listening so much quick, and I can't eat, I can't drink, I'm in the jail, she's left. Here we go. Oh, let's look at some surface water.
And go from creek to magnificent water and water.
Oh, it's good for you. Now, surface water. This planet is about 2/3, about 66% covered in saltwater oceans. Some parts of the world, oceans provide drinking water because they don't have any other good, reliable sources of water. And of course, for ocean water, it has to be desalinated first. You have to undergo evaporation or reverse osmosis, some process to remove the salt out of the water and to remove all the living things that are in the water. You don't need to chew water. But we'll look at that a little bit when we look at oceans and ocean coastline processes. Surface water now, what I want to focus on is flowing water, streams. To a geologist, the word stream means flowing water that's restricted to a channel. It's restricted to one place, to one channel. We're not for channel. One path, regardless of how big it is. So the little creek that goes through your neighborhood behind your house, that's a stream. Wolf Creek is a stream. The Mad River is a stream. Great Miami is a stream. Ohio is a stream. Mississippi is a stream. The Amazon is a stream. Brahmaputra is a stream. It doesn't care how big it is, as long as it's flowing and it's confined to a channel, confined to a space. Streams have a beginning and have an end. The beginning of the stream is called the headwaters. Water flows downhill, right? Which brings me to another point of clarification. South does not mean down. North does not mean up. That's coming from reading maps. And you're holding the map up like this so you can look at it and read it. North at the top of the map. And so that's north is up and south is down. And so you'll hear that in common speech. We're going to go up north. Or we're going to go down south and visit. We're going to go out west or back east. That's going all the way back to colonial days. It's just a reference to where you are in reference to the map. But north does not mean up. When you drive from here to Toledo, are you going up into the sky? No, you're going that way. When you go drive south to Miami for spring break, you're going down to the ground. Well, I guess it depends on what you plan to do when you're in Miami. No, you're going that way. North, south, east, and west, horizontal direction. Water doesn't have a compass. Water doesn't care as long as it's downhill. So streams can flow in any direction: south, north, east, west, south, southeast, north, northwest. As long as it's downhill. So the headwaters are usually going to be uphill in your higher elevations. Beginnings of streams, how does a river or stream even get started? We're going to be probably building some today, tomorrow, from rainfall. Water's trying to get downhill. It will take and exploit whatever easier free-made path is already there. You know, we've all been there. You know, you've had a long day and you're tired. You're hiking a trail out in the middle of nowhere. It's a lot easier to follow somebody and have them, trip over the logs first, get the spider webs in their face first, and the branches. Let them do it first, and then you're just behind going, oh, okay. Right? It's easier to do that. Water's the same way. There's a pre-made path downhill, so take it. Why do the work yourself when it's already been done? So every time it rains, that rain will flow along the ground, and when it does, it'll carve out a little groove in the dirt. Well, the next time it rains, that's where the raindrops go. Oh, look, there's a little groove that goes downhill. And they'll flow into it and flow down. Well, rain after rain after rain, the little groove gets bigger and bigger and bigger, and eventually develops into a stream channel. The farther downhill you go, the more water you have, so that little groove in the dirt gets bigger and bigger and bigger. Eventually, you'll get to the end of the stream. The end of the stream is called the mouth, because it's like an open mouth with the water, those fountains you see with the animals drinking, the water coming into the mouth. It's where the water comes out at the other end. That's what I want. That's what I want on my gravestone. So I want an image of me carved in granite with water coming. My finger up. I don't know.
Have you had your coffee this morning?
I haven't had anything yet this morning. I'm lucky to roll out of bed this morning. I had a really good weekend. It's kind of just rolling over.
Oh, were you first class?
Yes, you are. Yes. Sorry about that. Now, where the mouth at the end of that stream is, depends. It could be another bigger stream. It could be a lake. It could be the ocean. It could be a wetland, a swamp. It's wherever the end of that stream is. Wherever it stops, it's the mouth. The mouth is at base level. Base level is your local low spot. The ultimate base level is ocean or sea level. Once the stream reaches base level, its work is done. Most streams work, 24/7, 365, so technically they have no time off, they have no days off, they have no retirement. Hello. Sounds a lot like me. Streams have a job. Streams work. They do a lot of work and they don't get paid. Don't tell them that. Their job is twofold. And they're both very important. One is they drain excess water off of the land and return that water to other parts of the hydrologic cycle. Those streams can take that water back down to the ocean, and take it down to a lake, and distribute it throughout the groundwater system, can flow into areas and bring water to biological systems. It's a very important task. It's what helps keep the land dry, is the drainage from those streams. Streams do another very important job. I can grab the color I want here. Something different. Let me use this one. Second job of streams is to remove sediment. If it weren't for streams, we'd be up to our eyeballs. Sand, clay, silt, gravel. Nature wants a balance. It wants everything even. So anything that's above sea level, like the land, like mountains, is going to get attacked by weathering and erosion and get worn down. Anything that's below sea level, that's a hole, is going to get filled in and fill it up. Streams help with that. They help move the sediment made in the mountains down to all the local base levels to fill them in. That's a huge job. Streams help each other with this job. Yes?
So at some point then, this system, is it going to end up with the world's ultimately flat?
Assuming plate tectonics stops and the Earth's core is completely cold, we will probably completely level out the sea level. I mean, the land will be just at sea level. There'll still be oceans because they're so deep. There's not enough sediment on land to fill them completely in. I mean, nature's going to try, but we'd be pretty much at the land we don't have. So we don't have to worry about plate tectonics stopping at least for another 12 billion years. And some will probably go supernova and fry us all to a cinder in about 5. So. You win some, you lose some.
I'm not sure which I would prefer. Completely flat or barbecue?
Barbecue. I think we'll probably not be here to experience the barbecue. So remove sediment from the land. Streams help each other out doing this. Smaller streams will bring their water and sediment to bigger streams. Bigger streams will bring their water and sediment to even larger streams. So they help each other out. Each stream, just like each person with a job in a company or a business, each stream is responsible for its own area, its own set of responsibilities. The area that a stream is responsible for is called the drainage basin. It's called the drainage basin. It's also called the drainage area. It's also called the watershed. Sometimes scientists we get carried away with ourselves, we just keep naming the same thing over and over again. That's the area, the land area, drained by a stream and its tributaries. Again, streams help each other out. Now, small streams, okay, they're small streams. They can't do a big area. They only do a little bit because they're small. So little streams, you kind of think of as peasants or serfs, and they're all on their own little designated patch of land, and they're working hard, and they're draining water, they're moving sediment, and they're bringing all of that to the larger duke or earl or landowner. And they're bringing all of that to the larger stream. And the larger stream's taking all that in, and they're bringing that down to the king. And the king's bringing all of those bigger streams down to the emperor, and the bigger streams. They're bringing tribute. They're bringing their contribution of water and sediment to the larger stream. You know, you got that little tiny creek that flows through your neighborhood, and most people do. As developers, you know, they just reroute the creek somewhere else and they build a house around it. So you have a little tributary creek, a little small riddle of water that goes to the neighborhood. You know, every day that's gathering water and sediment. You know, maybe you're out there in Fairborn or someplace out there, and you got these little streams, and those little streams gather up all the water and sediment from their drainage basin, and they come down to the Mad River, and they say, "Oh, mighty Mad River, here's my tribute of sediment and water from Fairborn." Just think the Elkhorn neighborhood just over the corner. Thank you. So the Mad River collects all the water out of Fairborn and out of Beaver Creek and comes down to the Great Miami here, just outside of Dayton. And oh, mighty Great Miami River, here's my tribute of sand and water from Beaver Creek and Fairborn. Oh, thank you. Just put it over there next to the stuff in the Stillwater for me on North Dayton. Okay. And then the Great Miami River takes all that from the Stillwater, Wolf Creek, Mad River, the Little Miami, takes all of that tribute from southwestern Ohio, brings it all the way down to Cincinnati to the Ohio River. Oh, mighty Ohio River, here is my sand and sediment and water from southwestern Ohio. Oh, okay, thank you very much. And then the Ohio River takes that from the Great Miami River, from the Scioto, from the Muskegon, from like 2 other rivers, takes all of that, comes down past Indiana, past Illinois, down to Mississippi, and comes to old, mighty Mississippi, the great old man, old miss. Oh, just put it over there. Thank you. And then down that takes all that stuff all the way down to the Gulf of Mexico. That's tributary streams. That's what's still on the board here from Friday. That's going to be fun to take off. So here's Ohio. If you ever have trouble finding it on a map, look for a state shaped like an old pair of underwear. That's us. So that's Ohio. You know, it's well worn and stretched out, so it's, comfy. Here's Ohio. We're here. This dark blue patch here, that is southwestern Ohio, almost a full quarter of the state. A little bit of eastern Indiana and a little bit of northern Kentucky. That region drains as the drainage basin for the Great Miami. The Ohio River has its headwaters up here in the foothills just outside the Pennsylvania-Ohio border. And it comes down and picks up major tribute from much larger streams coming out of Pennsylvania, eastern Ohio, the Great Miami. The Kentucky River, Illinois River comes in here. And so the Ohio River has a much bigger drainage basin. It's responsible for almost 4/5 of the state of Ohio, plus portions of the Virginias, Pennsylvania, Kentucky, Illinois, and Indiana. And that comes down here to the Mississippi. Mississippi River has its headwaters up here in Minnesota. And the Mississippi River comes down here to the Gulf of Mexico. And it takes in all kinds of major rivers coming in off the Rockies, coming in out of the Great Lakes region and out of the eastern Appalachians. Mississippi River drainage drains almost 2/3 of the continental United States and drains it all out to the ocean here at the Gulf of Mexico. There are places along the Mississippi River where the channel itself is 1.25 miles. Why? Just the channel. Why is it so huge? Because it has all these tributary streams bringing in contributions of water and sediment from all over the country. It's good to be decayed. So those are tributaries. Any questions? How are streams moving all of this water and sediment? Well, the water part is easy. That's just gravity. The sediment is a little more work. If you've ever shoveled dirt, sand, rocks, snow, sediment is heavy. Streams need help to move it. And what they're going to get to move it is the water. The faster the water is flowing, the higher the velocity of the water. The more power it has. So therefore, the stream will be able to carry bigger sediment and it can carry more sediment. The faster that water is moving, the more force it has. The more force, the more able it is to carry material, carry heavier, bigger material, carry more material all at once, and bring it farther. You know, think about you. You know, you've had a good night's sleep, and you're all well rested, and had a big breakfast, and you're all ready to go, and yeah, all right, yeah, let's go. You're going to work, go to school, and you put on your coat, and you grab your 400-pound book bag, and you sling it over on your shoulders. Yeah, woo, go to school. And you get to school, and you run out of the parking garage, and you head up to math class, and yeah, and then you go to this class, yeah, and then you go to history, and then you got to go have lunch, and then you got to go to psych, and then you got to go to study group, and then you got to go to work for 3 hours, and then you get home, and what happens to the book bag? Okay, that's it. What happens to you? The same thing a little while later, right? You lose power. As you lose power and strength, your ability, your ability to carry anything drops. It's the same thing with water. If that velocity diminishes, it's going to lose its power. If it loses its power, it's not going to carry anything. This is one of the things that makes floods so devastating. When you have a flood, you have a lot more water, and it's flowing a lot faster than normal. That means it has the ability to carry bigger things and to carry more of them. People don't drown in floods. They die of blunt force trauma. They get battered to death by objects being carried in the water. Ooh, gosh, I got a nasty stomach. you want to hear the nasty story? I don't know if I told you the story before, the Johnstown flood. Johnstown flood, Pennsylvania, back in the late 1800s, one of my personal favorites.
How many people died this time?
Oh, hundreds.
That's a little low for me.
100 people. Yeah. Well, there weren't that quite as many people living there then as there are today. Hundreds. What happened is all the rich people had built this big resort spa up in the hills, and they had put in an earth dam, basically a dam made of dirt, to form a lake so they could fish and get in the boat and whatnot. Well, for years the dam was in deterioration and it was leaking periodically, and they were under pressure. Look, you got to fix this thing before it bursts. We have money. We don't care what you say. We'll do what we want. So, okay. Well, it was a huge, huge rainstorm. And the lake filled up well above capacity. So it rained and rained and rained and rained. And of course the dam burst. So then all of this water, hundreds of thousands of gallons, came roaring down the river. And it was a narrow valley. And the first thing it took out was this little community that was upriver. Took them out completely. So now the water's going down the stream. It's all full of broken up houses and debris from this little town. It comes slamming into the first bridge, tears the bridge down. So now you have bridge debris into the concrete bricks, I think. And that comes down. 30-foot wall of water comes down in this valley of Susquehanna into Johnstown. One of the first things it hits is the iron foundry. Now, iron foundries typically run 24/7 because it's a lot easier to keep them going than shut them down and start them up again. So this thing's running, and of course iron is very hot when it's melted. And if anyone's ever put a hot glass or a cold glass into a hot dishwater, what happens? It breaks. So when this cold river flood water hits these hot iron and steel crucibles in the foundry, boom, it goes up. So that goes through there. Now, what were they making at the iron foundry? It was the 1800s, big expansion west. They were making barbed wire, and they had hundreds and hundreds of rolls of spooled barbed wire ready to put on the train. Of course, see, the train yard is the next thing that the water took out. So now you had all of this debris and barbed wire and train boxcars and engines in the water, so it took the whole town out. There are accounts of people in the second and third stories of buildings trying to rescue people as they go by, trying to pull them out of the water. And they can't pull them out of the water because they're entangled in barbed wire. And the current pulls them down and out of their hands. And they're gone. There's a huge railroad trestle at the end of town. That's the port of train, right? Real strong trestle. The debris hit the trestle, but didn't break it. So all of the debris jammed up against this railroad trestle. And there are accounts of people still in their homes, smashed up in the debris against this railroad trestle, screaming for help. The people on shore can't get to them. And what's coming down the river towards the trestle? The trains and the locomotive engines that were picked up from the rail yard. And of course they're burning coal, and some of that coal is still smoldering, still lit. So that hits with all the debris and catches it on fire. So the rest of the townspeople spent the night listening to these people tracking the debris of the trestle, screaming as it burned, and they couldn't get to them to help them. They found bodies from that flood in the Ohio River over a year later. There were some people that literally lost their entire families, several generations worth at a time. The rich people were found to be not accountable. That's why laws change every time. Of course, nowadays they would be sued up the hill and back. But back then, we didn't have the laws in place yet to hold people like that accountable. Yeah, a lot of people. Many hundreds, if not thousands, of people were saved. There were these three men that saw the flood coming, and they got on horseback. And they literally rode the horses to death, trying to outrun the flood, yelling and screaming with their lanterns that people along the river did, flood, high ground, get to high ground. And they were credited with saving several thousand lives because people heard them. But they literally ran the horses to death. Typical horse, quarter horse, can run anywhere from 25 to 35 miles per hour. And they were able to just barely stay ahead of the flood. So They all got medals. They were the only ones. Yeah, isn't that awesome? That's a Halloween story for you. Yeah, we need to make a movie of that. Yeah. But actually happened. It's bad. And of course, it's a really bad story, but it's a horrible story again, because again, nobody gets held accountable for it. That's the kicker. That's why laws change. So again, the more water you have, the more power, the more force you have to move objects. And it's the objects in the water that's going to kill you. So on that note, let's see. What controls velocity? Gradient. And discharge. Gradient is your slope. It is the slope of the stream channel. If it's a steep slope, it's going to move faster. That's the whole difference between the extreme trail and the bunny trail. Right? That's the extreme. That's the difference between the little kitty slide and the big kid slide. Yeah. The slope. So it's a steeper slope, the water's going to be faster. Discharge is volume per time. It's a measure of how much water is in the channel during a specific amount of time. It's a volume measurement. The more water you have, the faster the flow. Another thing to remember in floods, when you have flood water coming over the road, don't drive through it. That water is flowing much faster than it looks. And you easily sweep your vehicle off what's left of that road. You don't know if the water has washed the road out from underneath. There could be no road there. You could just be driving into the river. And what four things are on most vehicles? Wheels. With a what on? Tire. What's in the tire? Air. What's air do in water? I mean, what do you use to sit on to float down a river? It's called an inner tube. Where do they get those? Tires. So a lot of times vehicles, when they get in the water, they're going to want to do this. Turn upside down because the wheels float. So then you're trapped in that thing and you're rolling upside down. Now, have fun getting out of it. Turn around, don't drown. Not worth it.
Maybe sure it's flat.
We do. Well, a lot of communities too, if you're caught driving around a road closed barrier, you can be seriously fined. Seriously. Because what it is then you're risking the lives of rescue workers to come and get you when you were told to not go there in the first place. It's like having a house on fire and you're going to go in, and then firemen have to go in and try to save you when you go in the first place.
I've seen cops pull people over in Ohio going around people.
Oh yeah, definitely. Yeah, you have to have proof. You have to have proof of residence on that street. So higher volume, higher discharge, water's flowing faster. Discharge is something that's going to be a frequently measured characteristic of any stream that comes anywhere near a city. That river down the street has a monitoring station on it, just about every 50 feet, 50 yards. And constantly it's measuring the depth of the water, the velocity of the water, the volume of discharge of the water. We keep track of that hourly, daily, weekly, monthly, seasonally, yearly. Because we want to use that information to help look for patterns, to help us in predicting flooding events, and to help us monitor the behavior of that river So we know what areas maybe need to be, where the dam needs to go in, or the dam needs to come out, or we need a higher levee, or we need to have dredging. It's a huge braided system. Glaciers too. The front of glaciers, we get seasonal melting.